So now let's take this example. Suppose that based on these two columns, x1 and x2, and based on some data, some training data, we want to capture this relationship between the target value and these inputs, I mean x1 and x2. So as a matter of fact, we want to build a neural network which can learn this relationship between x1 and x2. So you can see the actual relationship is x1 to the power of 2 plus x2 plus 1. But based on the training data, we want to enable the neural network to capture this relationship and understand this relationship. So as you can see, because the y variable is a numerical variable, this problem is a regression problem. So let's take this example. As you can see, we have two inputs, x1 and x2, and also we have two neurons in the hidden layer, and also we have an output layer. And as you know, each of these connections have some weights. And remember that we have the biases as well. So you can see that these are the weights W1, W2, W3, W4, W5, and W6. And these are the biases, bias 1, bias 2, and bias 3. So in order to do forward pass and also the backward propagation in neural network, so first of all, we should initialize these weights, for example, randomly. So let's initialize these weights. So we can see these are some random values. But now let's do the forward pass. Suppose that, for example, for these inputs, x1 and x2, we have a training data, which is 1 and 0. So suppose that this is the first data, and we want to update these weights and biases according to this data. So first of all, we should do the forward pass. What do I mean by forward pass? I mean, you should calculate the output of each neuron. So we can see we have neuron 1, neuron 2, and neuron 3. So we should calculate the output of these neurons. So let's talk about the neuron 1. So as you can see, the input to this neuron is 1 times W1 and also 0 times W3 and also the bias 1. So that's it. And if we plug in these values, we will get 1.5. And after that, we need to apply the activation function. And suppose that for this hidden layer, all the neurons in this hidden layer, we choose the ReLU activation function. So after applying the ReLU activation function, we get 1.5 because the ReLU activation function takes the input, and if the input is positive, it is going to return the value itself, but if it is negative or 0, it is going to return 0. But now let's do the same thing for neuron 2. So you can see that the input of neuron 2 is 1 times W3 plus 0 times W4 plus bias 2. And if you plug in these values, you will get 0.5. And after applying the ReLU activation function, you will get 0.5. So that's it. And now let's calculate the output of neuron 3. So you can see the input of neuron 3 is H1, I mean the output value of neuron 1 times W5 plus the output value of neuron 2 times W6 plus the bias 3. And suppose that we don't want to consider any activation function for this output neuron, or you can think of this as considering the identity activation function. And by saying identity activation function, I mean whatever which is the input, it is going to return that value as the output. So you can see that the output of this neuron is exactly the input of this neuron because we don't have any activation function. And the output of this neuron, which is the output neuron, is called y hat, I mean the prediction value. And now if we plug in these values, you can see that we get 2.5. So as you can see, the y hat is 2.5, but the true value is 2. So you can see y is 2 and y hat is 2.5. So y hat is the prediction value and y is the true value. So as you can see, this neural network should predict 2, but it has predicted 2.5. So there is a difference between whatever we have expected and whatever the neural network has predicted. So we want to update these weights. And in order to update these weights, we should calculate something called loss or cost function, which calculates the difference between whatever the neural network predicted and whatever which is the actual value. For example, here the actual value is 2, but the prediction value is 2.5. So for this specific problem, which is a regression problem, we can define the loss function as the difference between y hat and y to the power of 2. So we can see that y hat is 2.5 minus y, which is 2, to the power of 2. So the loss function, the loss value, the value of the cost function or the loss function is 0.25. And also let's show these values on the chart as well. So we can see the output of neuron 1 is 1.5, so that's it. The output of neuron 2 is 0.5, and the output of neuron 3 is 2.5. So you can see that we have calculated the output of each of these neurons. So the forward pass has been finished, but let's talk about the backward pass and also how to update these weights according to this data. So in order to do backward pass and also update these weights, so first of all, we should calculate the partial derivative of each of these weights. So for example, let's talk about W5. So you can see that we should calculate the partial derivative of the loss function with respect to W5. So in order to do so, we can see that the loss function is equal to this term, which you can see that it is y hat minus y to the power of 2. So you can see that this is y hat, I mean the prediction value, the output of this neuron, which we have talked about this one in the previous slide. So you can see y hat is h1 times W5 plus h2 times W6 plus the bias term. That's it, I mean bias 3. So you can see that this is y hat minus y to the power of 2. So this is the loss function. And if you want to calculate the partial derivative of the loss function with respect to W5, you can see this is the output 2 times h1. So this is calculating the derivative 2 times h1 times this parenthesis. And if we calculate all of these stuff, you can see that this value is 0.5 because this is y hat, which is 2.5 minus the actual value, which is 2. So 2.5 minus 2 is 0.5, and also times h1, you can see the output of neuron 1 is 1.5, and if you calculate all this stuff, you will get 1.5. So you can see the output of the partial derivative of the loss function with respect to W5 is 1.5. And after calculating the partial derivative of W5, so we need to update W5 using this formula. So you can see that the new value of W5 is equal to the old value of W5 minus eta times this partial derivative. And this eta is called the learning rate. And here is a question: why do we need learning rate? Because, for example, if you choose the whole partial derivative in order to update W5, then the weights are going to change drastically from one iteration to the other iteration. So in order to reduce this effect, we are going to use learning rate. And common values for learning rate is, for example, 1 divided by 10, 1 divided by 100, 1 divided by 1000, and etc. And also remember that this eta is a hyperparameter. And what do I mean by hyperparameter? I mean this is a parameter which is going to affect the algorithm, and you as the data scientist should choose the corresponding value, the proper value for this parameter. And of course, there are some algorithms which can help you to determine the proper value of these hyperparameters, and I will do my best to cover those algorithms as well in the future parts of this deep learning with TensorFlow and Keras tutorial series. And as I've said, the common values for learning rate is 1 divided by 10, 1 divided by 100, 1 divided by 1000, and etc. And for example, suppose that for this specific problem, we want to choose 1 divided by 100 for the learning rate. And also let's plug in other values. So the partial derivative is 1.5, and the old value of W5 is 1. And if you calculate all this stuff, you can see that the new value for W5 is 0.985. So now let's take another example. Suppose that we want to update the bias 3. So first of all, we should calculate the partial derivative of the loss function with respect to bias 3. So this is the loss function, and this is the partial derivative. So you can see it is 2 times 1 times this parenthesis, and if you calculate all this stuff, you will get 1. So the partial derivative is 1, and we should use this formula in order to update the bias 3. So you can see the old value of bias 3 is 0.5 minus the learning rate, which is 1 divided by 100, times this partial derivative, which is 1. And if you calculate all this stuff, you will get 0.49 for the new value of bias 3. And you can do the same thing for W6 as well in order to calculate the updated value for W6. So far you have seen that calculating the partial derivatives was very easy, but from now on, the calculating of the partial derivatives is going to get a little bit tricky. So for example, here, if we want to calculate the partial derivative of the loss function with respect to W1, so you can see this is the loss function, and if you want to calculate the partial derivative of the loss function with respect to W1, you can see that we don't have any W1 term in this loss function. So as you can see, the W1 is not directly in this expression, but as you know, the H1, the value of H1 is calculated based on W1. So in order to calculate this, we should simply calculate the partial derivative of the loss function with respect to the H1, and then we should use the partial derivative of H1 with respect to W1. So this is called the chain rule. Why? Because as you can see in this expression, W1 is not directly inside this expression, but for calculating H1, we need W1. So we are going to use this chain rule. And in order to calculate this, we should calculate all of these derivatives separately. So what is the partial derivative of the loss function with respect to H1? That's very easy. We can simply calculate this 2 times W5 times this parenthesis. And if you calculate all this stuff, it is 1. But how about calculating the partial derivative of H1 with respect to W1? So we can see that H1 is the output of neuron 1. And the input of neuron 1 is 1 times W1, so 1 times W1 plus 0 times W3 plus bias 1. So this is the input, and we should apply the ReLU activation function on the input in order to get the output of neuron 1, which would denote the output of neuron 1 by H1. So as you can see, 0 times W3 is 0, so this is equal to applying the ReLU function to this input, which is W1 plus B1. And again, here's the question, and the question is how to calculate this, because as you can see, the H1 is equal to the ReLU activation function of something. And as you can see, W1 is not directly inside this expression. It is inside a function. So H1, you can see H1 is a function of W1 plus B1. So as a matter of fact, W1 is not directly in this expression. It is inside another function, and that function is the ReLU function. So because W1 is not directly in this expression, and it is inside another function, it is inside the ReLU function. So once again, we should use the chain rule. And if you didn't understand that, don't worry about it, because we are going to explain it better. So in order to explain that better and better understand all this stuff, let's take another example to review the mathematics behind that. So for example, here we can see that y is sine of x to the power of 2, and we want to calculate the partial derivative of y with respect to x. So as a matter of fact, if you want to rewrite this, you can see that y is something to the power of 2. And that something is the sine of x. And in order to calculate this partial derivative, we need to use the chain rule. So we can see that the partial derivative of y with respect to x is the partial derivative of y with respect to u, that's something, and times the partial derivative of u with respect to x. So the partial derivative of y with respect to u is 2 times u, and also the partial derivative of u with respect to x is the cosine of x. And now in order to get the partial derivative of y with respect to x, we should multiply these values. So you can see 2 times u times the cosine of x. And because you want to write all this stuff with respect to x, so you can see u is the sine of x. So let's replace this. And you can see it is equal to 2 sine of x times the cosine of x. So let's go back to our problem. So as you can see, h1 is a function of w1 plus b1, and we want to calculate the partial derivative of h1 with respect to w1. So as a matter of fact, we can rewrite this as h1 is equal to a function of something, and that something is w1 plus b1. And as you know, this function is the ReLU activation function, and the ReLU activation function takes something, and if that something is positive, then it's going to return that in the output. But if the input is negative or 0, then it's going to return 0. So we basically said that h1 is a function of something, and that something is w1 plus b1. And now in order to calculate this, we should first of all use the chain rule. So we can see the partial derivative of h1 with respect to w1 is the partial derivative of h1 with respect to u times the partial derivative of u with respect to w1. And the partial derivative of h1 with respect to u is this. If you can see that if the input is positive, then the partial derivative is 1. But if it is negative or 0, then the partial derivative is 0. And also the partial derivative of u with respect to w1 is 1. So in order to calculate the partial derivative of h1 with respect to w1, we should multiply these. So you can see we should multiply this by 1. But because you want to replace all this stuff with respect to w1, so we should replace these values, these u's. So we can see u is w1 plus b1. So we should replace it, and you can see this is the partial derivative of h1 with respect to w1. So we can see that we have calculated this partial derivative, which is equal to this times 1. So this times 1 is equal to this. So let's plug in the values. W1 is 1, W1 is 1, and also the bias 1 is 0.5. So 1 plus 0.5 is 1.5, which is positive. So the output of this term would be 1. And the output of this term is 1, so 1 times 1 is 1. So as a matter of fact, the partial derivative of the loss function with respect to w1 is 1, and now we should use this formula in order to update w1. So you can see the old value of w1 as 1. This is the learning rate, and the partial derivative is 1. So if you calculate all this stuff, the new value of w1 would be 0.99. But now let's take another example, and suppose that we want to update the bias 2. So in order to do so, we should calculate this partial derivative. So this is the loss function, and we want to calculate the partial derivative of the loss function with respect to b2. But as you can see, we don't have b2 directly inside this loss function, so we should use the chain rule. And in order to calculate the partial derivative of h2, because h2 has the bias 2, so we can simply type the partial derivative of h2 with respect to bias 2. So if you calculate all this stuff, you will get this. And if I plug in these values, so you can see that this times 1 is equal to this. And if I plug in these values, you can see it is 0.5, which is positive. So because it is positive, it is going to return 1. So the output of this term is 1. So the value of this term is 1. And calculating this is very easy. The partial derivative of the loss function with respect to h2 is equal to this term, which the value is 1. So 1 times 1 is 1. So the partial derivative of the loss function with respect to bias 2 is 1. And now we need to update these weights, the bias 2. So you can see the old value of bias 2 is 0. This is the learning rate, and this is the partial derivative. So the new value for bias 2 is minus 0.01. So now let's take another example. Suppose that we want to update w3. So we should calculate the partial derivative of the loss function with respect to w3. So this is the loss function. And as you can see, we don't have w3 directly inside this expression. So we should use the chain rule. And as you can see, h1 has w3 in it. So you can see the h1 has w3 in it. So we can simply calculate the partial derivative of h1 with respect to w3, which if you calculate all this stuff, you will get this. And you can see this is this function times 0. So the output of this term, the value of this term is 0. So 0 times whatever, which is this value, is going to be 0. So you can see that the partial derivative of the loss function with respect to w3 is 0. So when we want to update w3, you can see it doesn't change, and you can see that w3, the new value of w3 would be as the same as the old value because the partial derivative is 0. So if you do the same process for other weights in order to update them, you will get these results. So you can see that these weights and biases are the updated values. So you can see this is the updated value of W1, this is the updated value of bias 1, this is the updated value of W4, and etc. And for example, if you have other training data, for example, suppose that this is the second training data, which you want to update these weights according to this training data. So once again, you should do all the stuff which we have discussed so far in order to update these weights according to this training data. And now maybe you ask a couple of questions. The first question is, how many neurons are enough for capturing this relationship? And maybe you ask how many layers of neurons are enough for capturing this relationship. And as a matter of fact, these things, I mean layers, the number of layers, the number of neurons are hyperparameters. For example, maybe for this specific problem, 3 neurons are better, or I don't know, for example, 2 layers of neurons are better. I don't know, we should check it out. And in order to check these things and in order to tune these hyperparameters, we need more programming knowledge of TensorFlow and Keras or other stuff, which we are going to talk about these kinds of stuff in future parts. And the other question that you may ask is, how can we choose the proper loss function for our problem? So for example, maybe you ask, what is the proper loss function for multi-class classification, binary classification, regression problem? And this is a question which we are going to talk about in the next part of this deep learning tutorial series with TensorFlow and Keras. Now I really suggest you to watch this video which is on the screen now.